segue in terms of spreading the love amongst different science disciplines. So the next discussion for the panel, kudos to the LEAG leadership for trying to integrate different realms of science. So we're going to talk about planetary science, life sciences, heliophysics, astrophysics, in terms of how the moon can help facilitate these scientific investigations. And this is something that I think through the discussions at LEAG this week and elsewhere, we're realizing we do need to integrate different science communities into this lunar effort. And that's something that Sam emphasized this morning during his opening statement as well. Okay, feel free to have a seat. I think there should be microphones. Okay, so thank you. Okay. I'll sit down here. So thanks in advance to the panelists for agreeing to come and talk with everyone today. So I will just moderate this discussion and hopefully I will fade into the background as a good moderator may. So what I'd like to do is just have each of our panelists give a brief introduction about their background, what your interests are, and then we'll start talking about some of the science. So, yeah.
Hi, I'm Dr. Kevin Sato. My background is in life sciences. I did my degree in biology related to human cancer and its mechanics and how it develops. I then joined NASA Ames Research Center in the area of space operations and implementations, where I worked with investigators to take their science proposals and turn them into space shuttle and ISS investigations, and then slowly moved into the area of space and life science strategic planning. And then currently I am the deputy program scientist for NASA Space Biology, and also the lunar exploration lead for space, life, and physical sciences research and applications in HEO Mission Directorate.
Hello, I'm Bob, or Robert McDowell. I work at NASA Goddard Space Flight Center in the branch referred to as the Planetary Magnetospheres branch, although well, because of the person who hired me 30 years ago, but most of what I do relates to heliophysics. The most recent heliophysics mission that I'm dealing with is I'm the magnetometer lead for Parker Solar Probe, and the magnetic field close to the sun is quite interesting. Related to what we are doing here, I am the deputy PI of Jack Burns' Survey NESS team, and in fact, that's why I'm sitting up here. Other missions that I deal with, I'm the principal investigator for the WIND spacecraft WAVES instrument and a lead co-I for the stereo spacecraft WAVES instrument. And I have worked on other magnetometer activities as part of the MAG team. So I guess I should make the introduction slightly longer to mention a couple of missions that we're working. I have a NASA-provided lunar payload, which is a radio spectrometer to be delivered to the lunar surface by intuitive machines. I'm also a co-I on Stuart Bale's LSITP lunar surface payload called LUCY, Lunar Surface Electromagnetic Exploration. And the NESS team, led by Jack Burns, is working on a lunar orbiting spacecraft called DAPPER, Dark Ages Polar Emitter Pathfinder, to do cosmology studies of in particular of the spectrum of the redshifted 21 centimeter line of neutral hydrogen. And beyond that, he has a probe class mission concept for an array on the far side of the moon that they call Farside, which has been developed by JPL. It has 128 antennas. It has spread over 10 kilometers, and it would make observations from 100 kilohertz to 40 megahertz, focused on again on the cosmology relating to the Dark Ages, et cetera, from the observations of the 21 centimeter line. But it will also detect the magnetospheric radio emission of exoplanets, which is something very interesting. And it will also do heliophysics, because the sun won't go away, even if you're on the far side. And there are other things, but that's enough time. Thank you.
Thanks. I'm Deborah Needham. I am at NASA Marshall Space Flight Center, and I, at my core, am a planetary scientist, planetary volcanologist, studying all of the terrestrial planets where I can find volcanic activity, which is all of them. And more recently, I've been focused on helping plan and plan the return to the moon, integrating science into the architecture across the spectrum of Artemis, so including Gateway, the surface operations, and going forward from there. So it's been a lot of exciting things going on right now, so that's what I've been working on.
Okay, so for the purposes of this conversation, you can see that the title of the session is called Artemis 3, Beyond Artemis 3. So when we're thinking about the science here, we're thinking about the 2025 to 2029 timeframe. These are activities that we're doing on the moon. Humans are there, so we've already got boots on the ground. So now we have the human assets, we have the robotic assets, there are commercial assets, there are international partnerships, all of the things we've been talking about today. So for this discussion, we're assuming that we have those capabilities in place. So what I'd like to do just to start off, and if there are questions from the audience during the conversations, feel free to get up and head to a microphone and we can splice you in as well. Just providing a brief summary of the types of science that you'd like to do on the moon, and in terms of educating everyone outside of our own fields of research. So what types of science investigations can and should be done on the moon, and why do we need to do them on the moon? So maybe Kevin, if you want to start from life sciences.
Sure. So for over past X number of years, we've been tied to the International Space Station, the Space Shuttle, which has kept us within the ability to study microgravity, but to really study partial gravity, we've had to use simulated devices in terms of centrifuges on ISS, which has been very rare, or we've had to use simulated radiation devices on Earth to kind of study cosmic radiation, solar flux, and other things in order to understand how radiation affects biology. From the perspective of physical science, perhaps I should start a little early in that. SLPTRA has 3 programs within it. It has space biology, it has physical sciences, which studies combustion, fluid physics, complex fluids and materials, and fundamental physics. So everything that we have done has stayed within the realm of low Earth orbit and have either been direct use within conditions that are dictated by what's on ISS, or conditions that we can actually take advantage on Earth with analogs. So what the lunar surface provides is actually being in the actual environment that we need to be in to understand partial gravity, especially 1/6 G. If we want to study it on the International Space Station, we do have some equipment, but we use a centrifuge. And so you're getting that 1/6 gravity, but also you're getting other types of components related to what happens when you have centrifugation. Also with being on lunar surface, you get the true deep space or radiation environment that we need to look at. So we can now look at microgravity, we can now look at combined effects. The other important aspect for us with using the lunar environment is that if individuals want to begin to use in situ resources, they want to be able to build stuff on the moon. A lot of the work that our fundamental physics groups do is to look at how things like glazing or soldering, or how materials or particulate matter crete, such as cement, actually work and function in a low gravity environment. And it's very different from what they're seeing in terms of combustion in those areas. For example, there's some papers related to that they've seen in microgravity, where the cement and concrete actually form a much finer and cleaner aggregate that appears to have a much stronger base to it, something you cannot do on Earth when they compare it. So now you go into 1/6 G. The question is what happens there? We really have no idea what happens in what we call the gravity continuum from between 0G and 1G. And that's an important aspect of also going to the moon. There are investigations that fundamental physics wants to do to take advantage of the lunar environment. Some are with laser ranging by having reflectors on carriers where they can hit them with lasers, sub-nanometer lasers, to look at field gravities. They also, one of the interesting things they are working on now in ISS, but now they can put it into a much extreme temperature condition as well. It's cold atom labs, and that's where they're taking Bose-Einstein condensates and forming them on station to start to look at and understand how at an atomic level, the quantum mechanics that occur at dark energy and other things. Well, this is still in the temperature of ISS where they have to cool things down. So if you put it into the cold of a lunar night, if they can maintain power, that could also help with getting more extreme cooling than they are able to get on station right now. They also want to look at different ways of using atomic interferometer for gravity gradiometers to look at ground penetration and substructure formation and other things. So there's a lot of different areas that we are looking at for the moon. From a life sciences perspective, as I've mentioned, we get real microgravity, we get partial gravity, and also, sorry, not real microgravity, but real radiation. And so we can start looking at combined effects. We can start asking the questions, if you try to grow a plant on the moon, does it still grow the same or not? If we utilize the regolith, can it grow the same way or not? The other important factors that we are also looking at initially would be with microorganisms. How do they spread? What's the microbiome of the built environment? You know, where we go, our bacteria go as well. And therefore, we want to understand how they change. We're collecting a lot of information related to the International Space Station, related to the microbiology that's on the station itself and how it's changing over time with different crew. Now, the moon provides a means of studying for the first time how that change starts from we'll call it a pristine environment, out to how it changes over time as it relates to human presence on the moon. And then beyond that, we may be able to bring up larger model organisms to begin to study how those effects are occurring, the general fundamental mechanisms by which the larger organisms are responding to, acclimating, and adapting. The important part is also bringing them home to Earth or bringing them back to the International Space Station and asking the question, all right, how is something that is held in a low gravity environment, potential long duration radiation environment, readapting to a 1G environment or a microgravity environment? And in this case, the question is really related to what can that do to inform our partners in the human research program for what things that they may need to now look at with regards to countermeasures. So it's a large partnership. But what I'm seeing here through this week, listening to everyone talk, is I think there's a lot of potential partnerships, collaborations, and ideas that you all have that I think initially one would say, oh, well, they're looking at the moon, they're looking at the geography, geology, there's nothing we can do with this. But in fact, when you look at what we are interested in, there is, I think, a lot of synergy and potential to develop that interaction between the groups.
Yeah, that's fascinating to hear you say that, because that's what I was thinking, taking notes about while you were speaking, because there are a lot of topics that we have discussed this week. Particularly, one example is in the resources group. So, you know, we're going to use resources, we're going to do construction, And so needing to know the materials science, needing to know how these materials are going to act in the lunar environment. We don't have, we need the expertise like this to look at that, and combustion as well. How does that actually happen on the moon? We need to know that. And another example is, the planetary protection work and how the microbes, spacesuits are going to leak, right? We're going to have microbes that are coming out when we have boots on the ground. So there has been discussions in some planetary protection groups saying, okay, well, how will that happen? Will it stay on the lunar surface? Will those microbes change? What's the distribution going to be? Is it going to change, as distance out from the landed assets? And so the work that you're talking about is somewhat addressing some of those issues too.
Yeah, no, exactly. And one of the things we do is obviously we do the fundamental research. We look at the mechanics and the mechanisms. But we're also realizing, and physical sciences already is doing this, is someone may say, hey, I want to do X. I want to apply Y on the moon, yet I don't understand A, B, and C. So how do I find that information? What do I do to get that research? And those are a lot of the areas that you're saying, Jen, that we can help and that we can do, and that our research is definitely in that area.
Yeah, that's great. Jerry. Yeah, if you can hop on a mic, because there's folks online too.
Jerry Sanders, NASA. So to pick on that a little bit, I tremendously agree about fundamental physics and understanding, say, better concrete and sintering. The problem is that we are stovepipe between fundamental physics and applied. So how do we break that? Because, working in the ISRU community, we're going forward with construction techniques and, different things like that, and just brute forcing it to some extent. So how do we embed fundamental physics folks? How do we design our early demonstrations for, say, a sintered pad or block on the moon with those fundamental physics questions or techniques to evaluate the product?
Yeah, I think it's going to start with building communications. And that's one of the things I'm on detail at headquarters to do, is to find who to communicate, who to work with. And I believe Frank Chiaramonte has been doing some communication. And they're busy with other work, but I think it's going to require a concerted effort to have that communication made.
Well, we got to somehow figure out a mechanism.
Yeah.
To that during solicitations or whatever, because I've had conversations. I've gone to the conference. I saw that there's another call for the conference coming up again, but it's got to be more than a conversation. Somehow we got to figure out a mechanism.
Yeah, and we've been talking about that, trying to figure out, all right, and we've been doing workshops, right? But you can only do so many workshops. Someone's got to say, all right, where is the funding? Where is the mechanism by which we can actually do something that's meaningful? And Craig Kondrot, who's our director, is certainly well aware of that. Devon Griffin, who is the new physical sciences program manager, is well aware of that. And so they want to start to build more than just a workshop. They want to see what they can do to begin to really put together something that now goes beyond and takes advantage of what's been learned to do something meaningful.
Yeah, and that was exactly to that point, that was one of the key findings from the resources and hazards subgroup at this meeting, is that the various entities, there needs to be a systematic integration of these different groups. And so it's being recognized. So hopefully we can get some traction on that going forward. And also, I'll add this to Kelsey's list. She's moderating the next panel, which will be discussing interactions between SMD, STMD, HUMD. So maybe they can talk about that as well.
Yeah, Dean Epler, Aerospace Corporation. So I spent 11 years in the Space Station Payloads Office. And that was a very productive, frustrating, yeah, the scar's still there. But here's the key on that, is that we had a key group of people, discipline-oriented, with a key group of engineers that understood what was going on with the vehicle. We were embedded in the program, and we were there full-time, 24/7. And workshops are great, meetings are great, but I'm really convinced the reason Space Station is so successful is that there were people worrying about this full-time, all the time, and paying attention not only to what the vehicle was doing, but what the guy in the next cubicle was doing. Because station turned out to be so complex that literally somebody turning on a switch on one part of the space station could cause your payload to brown out if it wasn't well coordinated. I don't think we need a payloads office yet, but in the end, the way you have to do it is to get lots of different people with different expertises in the same office all the time, working those integration issues so that, because even a month between this and that could lead to an irrevocable design change that then costs a lot of money to undo. So I think that, and that, so that system.
As part of proposal reviews and as a contract is going forward, on say a construction tech, somehow we could get, experts at the fundamental physics during that time.
Yeah. Yeah. I guess the point is simply it's a 24/7 job.
Oh, yeah.
Everybody's got to be dedicated to it. Right. Yeah. And it destroys your research career, by the way, because you don't have a chance to do anything but that. But it's really rewarding because in the end, the vehicle works, and it works because, you were there, knocking heads together or solving this problem or writing that document. So it becomes a complicated thing. It's a full-time thing, but it works.
Chris Pestek with USRA, just to follow up on Jerry's comment, just a suggestion, which you may want to do in the evaluation criteria for any future proposals, is to require maybe even teaming of investigators, one who is on the fundamental science side and the other who's on the applied exploration side. And so the evaluation of the proposal would be, okay, what is the fundamental science question that you're answering, and how is this applicable to ISRU, construction, whatever it is, and give them equal weighting. And I know it's very hard to break those stovepipes. Maybe you just force them together and cause those two communities to work together. Just a thought.
Yeah, that's something that we've had, at least on the life sciences side, discussions about, is looking at working across to the applications to the fundamental and trying to find common areas of interest that need to be addressed from both perspectives to make them both happen. So certainly well taken. Yes, we'll definitely do that.
I just wanted to add one more dimension to the conversations, please. I'm Jancy McPhee, and I'm with the Aerospace Corporation. In addition to the partial gravity and the radiation aspects, we are also hopefully staying on the surface for a longer period of time and really refining the details of how we're going to live in a closed environment, isolated with, it won't be nearly as dramatic as Mars, but it is a little bit different from our long-term stays on the ISS, and it's going to have science and health aspects and habitation aspects, and we want to keep our in-person geologists in good shape so they can carry out the science that all of you want to do.
Thanks. Yeah, I think those are areas that HRP, the Human Research Program, is looking at. Obviously, for us, to a certain extent, these are early days of trying to determine what we will do and what will be effective. And so there is the HRP Investigators Workshop every year where that would be a good area to bring up. From a life science perspective, from space biology, we definitely want to understand what that environment is like, and also how, whether it becomes toxic, whether you can actually engineer the microbiology on that to be a healthy environment. Those are questions also that our community outside of NASA are actually asking right now. So we're trying to we've been bringing in people who are remote to NASA and don't know anything about us into our community to start to address those questions as well, so we learn more.
So I am a life scientist, so I attend that meeting every year as well, but maybe one of you guys should come to that meeting also, or a couple of them, if we're talking about integrating and getting perspective, and I think that might be very valuable. And it's in January, so you can come to Houston.
All right, well, clearly there is a lot of activity and potential overlap and work to be done in the life sciences realm. So this is great. I think this is just the start of a closer integration between communities. So Bob told us a little bit about some astrophysics missions I want to make sure that we give Deborah time to tell us about the planetary science. We'll come back to you, Bob, I promise. But Deborah, I wondered if you could comment on, once we have boots on the ground and we're doing our planetary science, and Mark outlined some of the high-level science objectives, which, stood the test of time. So if you could comment on the architecture and the assets that you think would be critical to have on the ground, since you've been working a lot of the science integration with Artemis, and what are your thoughts on that?
Yeah, absolutely. So we've been directed to have a sustainable and sustained presence on the lunar surface by, 2024 first boots, but going forward from there, we want a sustained presence on the surface. And so that requires some sustained architecture on the surface, whether that's a habitat or some sort of pressurized facility. In generic terms, that's going to be absolutely required for a sustained presence. And like Jancy said, we want long-term missions to be a long-term presence on the moon, rather than a couple hours or 6 days or a week, a couple weeks. One of the benefits for going to the South Polar region is the number one resource that we have there is actually illumination, is solar illumination for extended periods of time. So taking advantage of that is going to be very important. So when you have a pressurized facility, you also need power. So we need some source of power. We've discussed this over the last couple of days, it's not going to be just one answer for one power source. We're going to need multiple power sources. Solar is going to be a key because we're going to have access to solar illumination for such long periods of time, but also having some other mechanism for generating the significant power that a sustained presence is going to require, not only for survivability of the crew, but also to facilitate the exploration around it, around the base or central location. So that leads to the next point, is you really absolutely need mobility. There's only so far that crew can walk in these bulky spacesuits, even the more capable ones that they're coming out with now. So we're going to need some sort of mobility. And you have options for that, many options that, the slate is, the plate is wide open at this point. Whether you have kind of like an LRV style unpressurized rover, or have a pressurized rover that we were exploring during the constellation days with the LEV, the Lunar Exploration Vehicle. Do you have one that gets you so much farther, or do you have a couple that allows you to have some redundancy? So if one breaks down, you can go pick up the crew and the other one and bring them back for safety. But also that gets you farther from your central location. But there are other ideas out there too. If you have, instead of having these vehicles that 2 to 4 people are driving around in, maybe you have an Antarctica style vehicle, like a Skidoo or a motorcycle type surface asset, where you have one person who's driving it and can kind of maneuver a little bit more, and then you tow your tools behind you, tow your instruments. So mobility is going to be very important, and that the distance that you require to go depends on where you go, what your location is, and how far it requires you to go to get to the location that you want to explore. Some of those stations, if you will be a couple kilometers away. Some will be 10 kilometers away, and some might be hundreds of kilometers away, requiring some sort of, either a hopper or some sort of asset that you can get to another location. These are all, ideas that we've talked about over the last couple of days, just kind of broadening the scope of access to the moon and getting away from just one location, do sortie missions farther afield. So these are all, generic ideas that we should be exploring as we go forward to try to plan these missions. The other thing that we need, in addition to these surface assets, are the tools and the instruments to do these amazing science investigations and address these really fundamental science questions that we have, not only for the moon, which is an interesting destination in its own right for planetary science, but also for life science and for heliophysics and astrophysics. But also the moon acts as a cornerstone for the planets, for the rest of the solar system. It preserves that earliest ancient history of what the solar system environment was like when the planets were forming, when Earth was forming, when life was developing on Earth. What was the environment like at that time? Those are still questions that we need answers to. So exploring the surface of the moon preserves that history, that record. And so we need to have the tools required to sample the right samples and bring them back. We need the instruments in place to take in situ measurements. We don't have to, not all of the questions that we have require samples. Most of them do require samples to bring back, but some of them we can address in place. We need those instruments there, and then the crew ability to deploy those and set them up and get them running so that we get the data back.
And how about a quick question about communications? So between Moon and Earth, between any base and astronauts out on EVA, where do we stand on that? Do we have a plan? Are we good? What do we need?
Yes, I mean, certainly communication is very important, as well as power and the other things that I mentioned. So communication is tricky. You know, I mean, there are ideas that we've heard this week, you know, having some sort of relay asset in orbit would be very helpful and would broaden the scope of where you can go on the surface. We've heard from James Carpenter earlier this week that, you know, the ESA is thinking about some ways to deploy satellites around the moon, a constellation of satellites that could support COM. So having international collaboration and contribution. There are also certainly commercial interests developing similar capabilities. So those types of capabilities will really facilitate communication from the surface back to Earth.
Hey, Sharon Kadar, JPL. So in the context of human presence and resource utilization, we haven't heard a lot about the prospecting tools, the geophysical prospecting tools that might be needed in order to, there's actually a crossover between resource utilization and fundamental science of the near surface. So I'd be interested to hear your thoughts about what kind of geophysical prospecting tools we would need, how we would go about making sure that these tools are, these tools serve multi-purpose, not just for resources, but also for fundamental science.
Sure. So to back up just a little bit before addressing your question directly, we heard from Nikki Werkheiser earlier this week. She was the leading STMD initiatives for ISRU and for extracting mineral resources from the lunar surface and near subsurface. And she was talking about, you know, two paths for retrieving volatiles. One is directly from the regolith, and instead of going to the permanently shadowed regions, you might be able to extract volatiles directly from the regolith, but then also going to the permanently shadowed regions where we think that these bulk concentrations of resources are, but they're much harder to access and harder to retrieve the materials. So there are two different paths. Before we go down those paths, of course, like you said, we have to find where these resources are. We think we know from orbit. So some of the first steps we need to do is ground truth those observations. And that's the Viper rover is one of the first steps to doing that, is to go and figure out what's the composition, what's the form, how is it sitting in the subsurface, how extractable is it. That's going to be one data point. It's roving, so it's going to be moving around, but it is one data point. It's not going to be able to access all of the areas. So potentially having additional landers with rover capabilities are going to be part of that story too, and we can take advantage of the CLIPS program to, you know, disperse similar types of instrument suites across the polar regions to try to figure out how do these resources lie? What are the resources and how do they lie in the subsurface and how extractable are they? So some of the instruments that are on Viper, of course, is a mass spectrometer, things like that. to try to figure out the composition and how it's sitting. If you want to get deeper in the subsurface, that's when you go to the geophysical instruments. Having a ground penetrating radar might be useful. It's a little tricky on the moon because you need a difference in material properties for a significant area to kind of detect that from a GPR. And the Chinese rovers did have a GPR on board, and that, it got some returns back. We got some interesting information about the ejecta blanket that it was sitting on, but it was pretty noisy. It's noisy data because the moon itself is very jumbled. It's a jumbled mess. So we have to figure out if we have a subsurface layer that would provide a return for an instrument like that. Then you also have, of course, seismometers that can get you some deeper information, or depending on how you're getting your seismic activity, how shallow and how deep those are, and how far away. So that's another way. Certainly, those are the types of information or types of instruments that we might have for geophysical analyses to see the distribution of subsurface properties in the near surface.
David.
Yeah, if I could just follow up and maybe augment what Deborah was saying. I've argued, actually, at previous LEAG meetings and other venues, that the crew rovers should, by default, have 2 instruments always on board for surveying, prospecting, and that's the ground penetrating radar, which Deborah mentioned, and a neutron spectrometer. And we've pointed out that you may have a crew mission on the surface for 14 days or 42 days, but that asset remains there the whole year. And so you could telerobotically prospect with that tool in that intervening time. We actually, for those of you who don't know, the LPI installed a ground penetrating radar on the Lunar Electric rover during constellation, and it was operational during the DRATS mission simulations in northern Arizona. We didn't have it tied to the interface that crew were actually using, but we had because it was a tech demo, we had that feed to our investigative team. And it was a very robust instrument. It survived the entire mission sim, and it looks good for lunar deployment.
Yeah, David brings up a very important point as well. With the rovers, crew's only going to be there for a certain amount of time, and hopefully it's going to be an extended period of time by 25 to 28 and beyond. But when the crew isn't there, you still do have these surface assets available. And one crazy idea that I have personally is that you have your rover that the crew is driving around in, but when they leave, maybe before they leave, they install an instrument suite that might be a little too sensitive for the speeds that the crew might be driving, but you install an instrument suite that you want to telerobotically rove around the surface for longer terms, like David was saying, and take advantage of the fact that that surface asset's still there. You can drive it, if it's solar powered, for example, you still drive it into the sunlight, follow the sun around and characterize the area, but taking advantage of the time that you still have assets on the surface even when crew is not there.
Again, just to address I think the fundamental question, which was, what instruments could be used, and making sure that they tie to both science and potentially resources. So as I mentioned yesterday, there is a team going on within NASA that is actually looking at that kind of question. From an ISRU point of view in particular, in terms of what instruments and what types of measurements are needed to eventually assess ore bodies, whether it's permanently shadowed crater, ice, or regolith, compare them to surveys that have already been done from a science perspective, compare and contrast and see where the overlap is and where the gaps are. So hopefully that report will come out before the end of this year at least, or early next year for vetting and community input.
Great. Thank you, Jerry. Thanks, Deborah. So we have a couple of minutes left since we started about 5 minutes late. So I promised we'd circle back to Bob. And just wanted to ask you, so there's some on the realm of heliophysics and astrophysics. You described some missions concepts that are pretty far advanced, like DAPPER and FARSIDE. I'm wondering if you can comment on the role, if any, of the commercial partners and the international partners in those missions as we think about going forward to the moon.
Okay, well, I just mentioned a couple of specific missions. But I would say that for the vast majority of scientific activities on the lunar surface, there will be commercial involvement, and in many cases, international cooperation. Just considering, for example, the Far Side Array for radio astronomy, which has been discussed for a long time. There are several countries proposing to do this, and well, obviously it would, in some ways, be a little smoother and better if they work together. At this point, I'm not aware of that really taking place yet, but perhaps as everything advances, that will be the case. So the Far Side radio array is back there in order to for the moon to block all of the radio transmissions that come from the Earth and arrive at the lunar surface. So if you put your radio astronomy array on the near side, the sensitivity will be low. You could still do studies of solar radio bursts, but you would not be able to observe astrophysical, cosmological, and extraplanet sources. So, in any case, also the larger the scientific instrument or something, the greater the need for involvement from commercial sources to create something which will fully function. The Far Side Array, which to date JPL has been doing the design for, has antennas that are distributed over 10 kilometers, connected to the base system by fiber optics. And of course, there has to be a rover that goes out and sets those approximately 128 antennas over throughout the region. Most of what we're talking about is the lunar surface, but there are also orbiters, and again, commercial companies play a key role there, as they will in some of the CubeSat missions that and small sat missions that you've heard about in the last 2 days, and Jack Burns et al.'s Dark Ages polarimetry pathfinder will have commercial involvement. So I think the answer is almost always.
Super, thank you. Well, we're almost at time. I just wanted to give the panelists 30 seconds. If there's any thoughts that you wanted to share with the broader audience before we move on to the next session. So if you don't, it's okay too.
Yeah, no, I think for me, this has been really eye-opening to see what the potential for collaboration and real collaborations are, certainly radiation in different areas. I was at a LEAG meeting years and years ago as a sole life science representative, and it was very interesting. At that time I was a contractor, so I had to be careful. But certainly it's great to rejoin this community, and certainly when I get back to headquarters and I talk to the folks, I really want to start to build the bridges out to the community.
Excellent, thank you. Bob, any last thoughts?
Yes, well, as was mentioned a little earlier, one of the key areas is having relay capability to get data from the far side, and so one component that we thought was going to play a key role was the NASA Gateway, and I might have missed a talk, but I haven't heard much about it today. Is there anybody in the audience who wants to say something about the Gateway?
There will be a panel coming up after this one
okay.
that will be addressed at. So
very good.
Thank you for introducing Kelsey's panel. Deborah?
Yeah, I mean, really, we live in exciting times. And I mean, we've said that over and over, and I don't know, the enthusiasm in the room, it might be a little tired this morning, but over the last couple days, it's been really exciting to talk with you all about, you know, our science goals and across the disciplines for planetary, but also bringing in the other sciences is really important. It's a truly cross-community effort and global effort, even with our international partners and commercial entities as well. And we're all going to work together, and we're going to go back to the moon. We're going to explore farther into the solar system. And it's really exciting, and we're going to work together to do it. We have to work together to do it. So.
Excellent. Thank you. Well, join me in thanking our panelists. Appreciate your time.